In this work, we focus on training video language models from video-text pairs. We propose LaVilla, a new approach to learn video language representations by leveraging large language models. We achieve this by repurposing pre-trained large language models to be conditioned on visual inputs, and then fine-tune them with human narrations to become automatic video narrators. The auto-generated narrations offer several advantages, including dense coverage of long videos, much higher diversity of text, and compared to human annotations, generating narrations from large language models is free. The video language embedding learned contrastively with these narrations outperforms the previous state-of-the-art on multiple first-person and third-person video tasks, both in zero-shot and fine-tuned setups. We dive deeper into the details of the approach. We use a dual encoder model to learn video language representations. It contains a video encoder and a text encoder. For video encoder, we use transformer, where we initialize the spatial attentions using clip pre-trained model weights, and then the temporal attention with zeros. For text encoder, we use a GPT-2-based transformer, which is also initialized from clips model weights. On top of both video and text encoder, we use a projection head to obtain the global visual and textual embeddings respectively. A contrastive loss, such as InfoNCE, learns global embeddings that associate corresponding video and text embeddings within a batch of samples. The pre-training data, including both human annotated video text pairs and then pseudo-captioned video clips. The pseudo-captioned narrations take advantage of large language models' supervision from two aspects, namely rephraser and narrator. Rephraser is a standard large language model that paraphrases narrations in existing clips. It serves to augment the text input. Narrator is a visually conditioned large language model that pseudo-labels existing and new clips with narrations. It generates new descriptions of the action taking place and can potentially focus on other objects which humans are interacting with. We provide two examples of the output by rephraser and narrators on the right. Rephraser is a text-to-text model implemented by an encoder-decoder architecture, such as T5. We observe that rephraser can do basic manipulations, such as replacing synonyms or changing word order, which serves as an efficient way of automatic data augmentation. Narrator contains a visual encoder and a text decoder with attention pooling in between to align the dimension between vision and text. The text decoder follows standard large language model such as a GPT-2 large model. This enables narrator to be initialized from pre-trained weights, taking full advantage of large language model's capacity. We add a few additional cross-attention modules before each of the GPT-2 block to provide visual conditioning. We keep the GPT-2 transformer blocks frozen and only fine-tune the cross-attention modules in between. The visual encoder to generate video embeddings for conditioning are obtained from the dual encoder model's visual part. We train the narrator on all or subset of human annotated video narration pairs using captioning laws. During inference, we query the narrator by feeding the visual embedding and the special start-of-sentence token. At each time step, the text decoder produces a likelihood over all possible tokens in the vocabulary set. We use nuclear sampling in an autoregressive way until a special end-of-sentence token is reached. This process can repeat for multiple times to generate diverse narrations. Here we describe how the narrator densely narrates the entire long video. For existing video clips that have been annotated by human, we directly recaption them. For the remaining part, we first uniformly sample video clips from unlabeled intervals and then densely caption on these clips. Next, we filter out clips with low similarity score between the video clips and the generated narrations using a pre-trained dual encoder model. We train both the narrator and the dual encoder model on the video narration pairs from Eagle 4D videos that are not in the validation or testing split of the Eagle 4D benchmarks. The pre-training dataset includes around 4 million of human annotated clips with an average length of about a second. With the help of narrator and rephraser, we expand the narration corpus by 10 times and 3 times respectively. We conduct zero-shot or fine-tuning experiments on a wide range of downstream benchmarks, including Epic Kitchen 100, Eagle 4D benchmarks, EGTA, and Charade's Eagle. In the zero-shot setup, we apply the pre-trained dual encoder directly on the downstream validation split without any tuning. In the fine-tuned setup, we take the pre-trained dual encoder and perform end-to-end fine-tuning on the training split. The resulting model learned on these expanding narrations sets a new state-of-the-art on a wide range of downstream tasks across challenging datasets. For multiple instance video retrieval on Epic Kitchen 100, we achieve a 7.1% absolute gain on average NDCG after fine-tuning. For multiple choice question answering on Eagle 4D, we achieve 5.9% absolute gain on intra-video accuracy. For video recognition on EGTA, we achieve a 10.1% absolute gain on top 1 accuracy after fine-tuning. We observe positive scaling behavior on increasing pre-training data and model size. For data scaling, we can see a consistent performance gain with increasing pre-training data. Notably, La Villa trained with only half of the narrations from the Eagle 4D dataset outperforms baseline models trained on the full dataset. For model scaling, we compare the zero-shot retrieval result by progressively increasing the size of narrator's video encoder from transformer base to transformer large while fixing the dual encoder architecture. The retrieval performance steadily increases while narrator becomes stronger. We also vary the dual encoder architecture and show similar trends. Both phenomena suggest that La Villa can scale to larger models. For more details, please check out our GitHub repo and play with the demos that are available online. Thanks for watching.